Good morning, dear students. Today we will be discussing few numericals and we will see how simple harmonic motion concept can be applied in different aspects regarding circular motion. First, we will start with the discussion on circular motion, and then we will move to discuss some numericals. If the time permits, then we will start with numericals also. So let me see, let me share my screen. Just a moment. So I hope all of you have gone through all the parts of your discussion regarding the simple harmonic motion, and all are comfortable in discussing all these things. And I hope that many of you are now able to understand the simple harmonic motion, and all of you can apply also this part. So I hope now you can see my screen. Is it visible? I hope so. Okay. Just a second. Yeah. So this is it. So I hope now you can see it. I think yes. Yeah. So we are into the sixth part of our second module, oscillations, and we are discussing simple harmonic motion. And we have discussed many of the parts of simple harmonic motion, but this is the first part, the introduction of simple harmonic motion is the first part of second module, oscillations. Damped oscillations, forced oscillations, and their mathematical analysis, and resonance we will cover after these SHM is over. Myself, Dr. Pradeep Sharma from University of Engineering and Management. You can note down my contact number and email ID in case of discussing any problem or doubt regarding this topic. In oscillation module 2, we are into this free vibration part, and forced and resonance and other things we'll see later. All these topics we will be covering one by one. Today we will see how this uniform circular motion works actually, and we'll try to see that whether there is a relation between simple harmonic motion and uniform circular motion or not. Okay, so we can see that there is certain relation if any object in simple harmonic motion has the same motion as of an object in uniform circular motion. You'll kindly see this. I hope. So I hope you understand this, that a uniform circular motion can be considered as simple harmonic motion when we are seeing it from the side, and it is taking in the same way the oscillations as in SHM about the mean position. See, so here you are seeing that this object is taking the circular motion, but its projection on the wall, the shadow, is actually taking as the same oscillations as simple harmonic motion around the mean position. So I hope it is clear that when the extreme position is to be taken care, then we have to see the function in different manner, and when the position is starting from the origin, then the different function is there, right? So a sin omega t in case when it is starting from 0, and a cos omega t when it's starting from the extreme position. Now I hope you understand that how a relation between uniform circular motion and SHM can be derived by using the concept of phase difference in between them. So if we consider the particle in uniform circular motion with radius a and angle phi, so we can write like a cos phi is the displacement, and the angular velocity is d phi by dt. So phi is equal to omega t at any instant initial moment. So we can say that particle in uniform circular motion with radius a and angular velocity omega. So if it is moving like this, so a cos phi, and easily we can make out this as a projection over here. So this way we can easily correlate with the circular motion, and having on the this axis minus a to a as the extreme positions, and this projection of a cos phi we are getting from here. So you can see that the projection is actually going like this over here, and it is moving in this direction and this direction, right? So this way we can assume that there is a clear relation between circular motion, uniform circular motion, and simple harmonic motion. So these relations we can easily find out for velocity and acceleration of this part. So this way I hope it can be understood very clearly that when we are uh, creating this uniform circular motion with initial angle phi naught, so the phase angle will be omega t plus phi naught. So this will be the angle at any time. So this will be the phase angle at that particular instant of time for the particle taking uniform circular motion. For example, if we can consider here this very important example, you kindly consider this. So I hope this concept is clear, because the radius will be high, and when the radius will be high, the rotations, we can say the frequency will be decreased to maintain the centripetal force, because centripetal force should remain constant You can see this example also. So I hope you understand all the topics here, what been described. That whenever circular motion is in place, so there will be a force maintained at the, towards the center, and the motion of the object which is outside, outward, that is actually you can say managed by that centripetal force, so that that object is not coming out of that circular path. So I hope all of you must understand that in a vertical circular motion, if there is some tension and there is a weight of an object is taken care of, so while taking the circular motion, so at the bottom there will be 3 times of the tension, 3 times of the weight. There will be we will experience, and that object will be experiencing that much amount of force to maintain the motion in circular. So this is all due to the fact that suppose the mass of this, the weight of this person is suppose 100 kg. But when it is at the bottom of its circular motion, it is actually facing a force of 300 kilo, 300 kilogram. So you can understand that to maintain that force, it's very impossible for that person. His arms should be very strong to maintain that. So this way, I hope you understand that how the simple harmonic motion can be related to uniform circular motion, and what are the challenges for uniform circular motion to maintain related to the centripetal force, and how to maintain that, and what type of forces the object can experience. So in the next class, we will see the numericals based on simple harmonic motion. Thank you. Thanks.